Okay, welcome back. And now we'll have the third lecture of the series by Dmitry Noshchenko.
Hello, hello. So today we continue studying operations on symmetric quivers, and just a quick recap. So last time we have discussed unlinking operation, which in the most simplest scenario relates this pair of quivers, and effectively it removes a pair of arrows and adds an additional node, which has some number of loops and connections to other nodes of the quiver. And yeah, so this is the general definition that we had. And the theorem states that by comparing quiver generating series, so they are equal. So before, for a quiver Q, and after unlinking of this quiver, so these generating functions are completely equal for any quiver. And so maybe let me just give you some example how this more general case so because we have studied this simple scenario, but let me just give you a slightly more general case. So the next example would be the quiver, which is very similar, but let's add one more node here. So let's again consider pairs of nodes which are connected by pair of arrows, and let's also connect in a similar fashion the third node. So you can write adjacency matrix. And now we want to unlink it, and we want to unlink it several times, not just once. So let's first, we can put some decorations here as usual. So let's say that this node corresponds to x1, this node is x2, and this node is x3. Here we have x1, x2, and x3. Yeah, so now let's hit by unlinking. So let's apply operator uij, and I will write, let's first apply u12, for example. So we can apply it first to the matrix, and what it does. Again, so we have 1 and 2, and we have to remove the connection between 1 and 2, so we get 0. So the rest of the matrix stays the same, so the third node is unmodified. But we have to add one additional generator, and in this case, it is equal to sum of the values of the loops at I and j plus 2 times the value of Cij minus 1. So it gets equals to 1 here. And the rest would be just 0, 0. And here we have 1. So we have applied it once, and so the vector of generating parameters accordingly is modified as follows. So if we apply u12 to x, so this just gives us again x1, x2, x3, and the new variable is q inverse x1, x2. So the new variable which sits here, so maybe I can also just write it here. So this is q inverse x1, x2. So this is x1, x2, and x3. Yeah, so now what we can do, we can continue hitting by unlinking. So let's just know that here we have, again, so this was the connection that we have put by hand before. So this is this pair of arrows, but we also created a new pair of arrows. And in principle, now one can iterate unlinkings. And yeah, maybe just let's compute the next iteration as an example. So let's compute u23 combined with u12c. So in this notation, we first apply u12. So we get this guy, and then we hit by U2, 3. So the resulting matrix is as follows. So the first 3 by 3 block would be fully unlinked. So we get zeros. So this block corresponds to the initial keyword that we had here. And now, of course, we have this additional generator, which was 1. And the connections here stays the same. So here we have 1, 0, 0. So this is unmodified. And we again have a new generator, which you can compute. This is 1 as well. And here we have 1, 1. And if I did everything correctly, so it should be zeros elsewhere. So you see that in principle, if one hits by unlinking and then continues iterate, so it creates more and more arrows. So again, we have this new pair of arrows which has been created. And we have these ones which have been created in the previous step. So the question is, so can we make somehow this procedure to be diagonal? So can we make some sort of an infinite product of M-loop quivers when we just iterate on linking? So the answer is yes, and in fact, we have it as a theorem. So let me just formulate it. So the theorem is that given a quiver Q, so Q is arbitrary, and so for any quiver Q, one can write the generating function, material generating series, as a product over some infinite set, which we denote Q0 infinity. And the product is taken over M loop quivers, essentially. So this is CI infinity loop xi and q. So what this theorem gives us is that so any quiver could be essentially diagonalized. So in principle, if you start with some complicated quiver which have many connections, so it could be like any number, so any number of nodes. So then if one applies subsequently unlinkings, and generically we have to apply them infinitely many times, but one can show that applying them in a special sequence, so then this procedure actually converges. And so the result would be just infinite union of M-loop quivers with some number of loops. So it could be 1, like could be 2, 3, 0, maybe then again 2, and so on. So these numbers, they're generally hard to deduce exactly, but there are some combinatorics involved, of course, and you can compute it for any quiver. So I will not give you now the proof, so maybe I can return back to this theorem sometime later. So if I have time, because so for the moment, I just wanted to mention this as a very useful application of unlinking. So what we can say new about the structure of the material generating series. And yeah, so maybe I can just mention that this procedure allows for effective computation of omegas. So one can compute the motivic DT invariance from this diagonalization procedure, and one can also prove integrality, prove that they are integer numbers. So based on the knowledge that M-loop quivers obey this integrality property. And this can be proven by using some recursion. So the next thing that I want to discuss is, so maybe let me Yeah, maybe let me ask if there are some questions. Okay, so yeah, let me then erase this. And we'll move to something else. So the next thing that I want to discuss is Quiver equivalences. Yeah, so based on the fact that we have now this unlinking operation which acts on symmetric quivers, we can study the structure of quivers which arise from unlinking of the same quiver. And so first thing that we can define the equivalence relation, but we can define it in slightly more general way. So it will be more general than unlinking. So you will see in a moment. So we define the two quivers, Q and Q prime, to be equivalent. If and only if we have the equality of generating series. So if P of Q of x1 to xm, so where m is the size Q0, I can set m prime as size of Q0 prime. So when P of Q equals to P of Q prime with some other generating parameters, but we allow here for, so this equality must hold when these parameters are related in some way. So we have to put xi prime equal to Q alpha I0 times. So if there is some dependence of these parameters, alpha I1, alpha IN. So this is the general thing, and you can immediately compare it with the definition of unlinking and say that, so unlinking indeed generates equivalences, but perhaps it's not the only source of such equivalences. And in fact, we don't know if unlinking covers all possible equivalences. So this is an open question, but for the moment, yeah, so we will focus only on unlinking. And so let me define the next object. So next we can study all unlinking operations, and we can define what we call unlinking monoid. So this would be given by some generators, and generators are essentially unlinking operations, Uij, where Ij is some alphabet that labels all possible nodes. So this is just like some convenient set of labels. For example, could be like the set of integers. Yeah, and this just to make it work nicely, we can append it with operator which kills the quiver. So we can define this like a zero element. So this gives the quiver whose matrix is empty and whose vector of variables is also empty. And we can consider all possible compositions of such operators. So essentially elements, what are the elements of U? Of U are sequences of unlinkings. And in principle, now we can study the structure of this monoid without referring to a specific quiver, which is a big advantage, and it allows to uncover many interesting properties of unlinking. So from now on, let's consider Q to be generic. So all quivers that we consider would be completely generic. And we're only interested in the structure of unlinking operations, not in the structure of particular quivers. And what the first thing that we can say about these operations so one can ask what happens if we have we can write another way. So what if we hit some generic quiver by unlinking URJ, but after we unlink by some other pair of nodes like K and L? So can we say that, well, these two operations commute, for example? So that is it equal to UIJ, UKL, Q? So, yeah, any question? Yeah, so the answer is yes in this particular case, but there is an important assumption to be made. So in fact, this commutativity holds if and only if. So all these indices I, J, and KL all are distinct. So of course we have the condition that I and J are distinct because we want to unlink different nodes. So I is not equal to J in principle and K is not equal to L. But we also have here that in order for this to hold, we must to impose that I is not equal to K and J is not equal to L. So I will now introduce some diagrammatic notation, which is very useful when we study the structure of unlinking. So essentially, this commutativity we can draw like a square diagram. And so these dots would be quivers, and in principle, you remember that you can put any quiver here, and this diagram computes automatically. So the quivers are generic, so Q is generic. And here we just put indices. Let's put them in brackets. So let's put them IJ here, KL. Here we have KL and IJ. So now the question, what happens? Yes, so why this condition? So what happens if these indices are equal? And the next scenario, so let's say when we have, so I'll draw it as a diagram now, and So let's say we hit here by uij, and here we hit by jk. So one can show that this diagram becomes a hexagon, and we have the following picture. So here we can apply jk. Here we can apply ij. And here we need to apply, so I will write, okay, let me write in this bracket notation, and ijk. And from this side we have sorry, another way around. Because we hit this guy first, so this I, J, and K. And here we have I, J, K. So in order to so let's just write it in a proper way as a sequence of unlink is applied to a quiver. So if you have a quiver Q, and if you hit it by U, I, J, so then we hit U, J, K. So then we need to hit by unlinking, which takes first the node which has been created when we unlink ij. So this node is effectively response to Q inverse x I xj. This is n. And the second node here is simply j. Oh, k, sorry. So here in this case it's k. Yeah, and if you inverse it, so then we just inverse here I, so here jk. And these two guys are permuted, so we have ij, jk. So this is what we call the hexagon relation. And one can also write the second type. So this is type 1. And type 2 would be very similar, but slightly different order of operations. So type 2 would be the following. So we apply, so start is the same. So we have ij, jk here. But now we invert the ordering of these two operations. So we permute this and this. So here we put first ijk. So then we put jk. And here we put I, jk. And here we put ij. And interestingly, so this type 1 and type 2, they're not the same. So the resulting, so if you put here and here the same quivers, so then the resulting top quivers, they're not the same, but they could be unlinked once more, and you obtain the same quiver. So you need to apply one more operation, and then you get the same result. But otherwise, they are slightly different. But nevertheless, of course, they're equivalent by our definition. So the generating functions of all such quivers, they're completely the same. So these are essentially the three relations that we need. So we have one just commuted in square, and then we have two types of hexagons. And now, given that, now we can study more general sequences, and we can say something more about structure of these sequences. Oh, I see some question in the chat. Yeah, so she asked if there is a node with infinitely many loops, then this node can be deleted. Yeah, so the node with infinitely many loops, yeah, so it's yes, in principle, just let me just go back. Oh no, I erased it already. But okay, so yeah, so if you have infinitely many loops, so then yeah, we can say that this is like the empty node. Well, in principle, this algorithm it does not produce like infinite loops, but it produces like step by step. So yeah, if I just if you think about this algorithm of constructing Q infinity, so then essentially you can think of it as computing omegas, so dt invariants, and they would be indexed by some number n, and eventually n approaches infinity. So then term by term, there is some stabilization, and this series could be computed term by term. And yes, so you can think of this infinite loop as just being discarded afterwards. Yeah, so going back to unlinking relations, so what can we say yeah, about such relations? So first of all, so one can ask if we have sequence of unlinkings, which we can denote like ij, and we can put here like a vector. So this is usual notation that we use for sequences. So here would be I m, j m, I1, j1. So one can ask if there are more general relations which cannot be deduced to these three simple types that we have described above. And the answer is no. So these three simple types, they form complete set of basic relations. So any relation of the form uij close to ukl can be deduced or maybe better to say can be so maybe let me state it a bit more precisely. So given a relation uij equals to ukl, where ij and kl are sequences, so we can find we can always find a sequence of square and hexagon moves. From first sequence to another sequence, from uij to ukl. And so essentially it states that if you have some more complicated shape, or we can like form some very, very complicated long diagram, and if this diagram closes up, so if you have a relation, so we have something like this, so then the interior of this diagram, we can always tile by these simple tiles, which are always squares and hexagons for any relation that we have. Yeah, so this is property one. And so the property 2 would be as follows. So now, again, assume that we have Uij, UKL. But now let's say that they do not form a relation, but rather they are organized as follows. So we have some starting quiver, and we apply some sequence of unlinkings, and this would be, so this part would be Uij. And to the right, let's apply UKL, and this gives some different quiver. So here we have UKL. And now the statement is that for any such Uij and KL, you can find, also not unique, but you can still find U K prime L prime and U I prime J prime. So some pair of different sequences such that this diagram is completed to a relation such that UKL K prime L prime combined with Uij equals to U I prime J prime combined with UKL. So we call all such pair of sequences a connecting sequence or a connector. And by diagram, so this connector simply completes via some number of steps, completes the diagram into a closed diagram. So that we have a relation, and yeah, so the theorem that now it holds for any such a pair of sequences. And yeah, so I will not give you the details of the proof now, but maybe later if the time permits. But now just let me give you an example how the sequences can be connected. Because in principle, the statement that there is an algorithm to compute the connector in a finite number of steps. And just to give you a simple example, so let's take this example. So let's assume that here we start from some generic quiver whose size is 3. And we can apply, yeah, maybe I could say the size is 5 because I put the index 5 here, but yes, let's say that. So the size is 5. And then we can apply, so this is our Uij in KL. So Uij is U1, 2 first, and then U4, 5. And UKL is just one unlinking, so this is just U2, 3. Now let's compute the connector, but now we can do it stepwise. So let's note that we have a pair of unlinkings which share the same index, which means that we can apply the hexagon relation. And we can close up the picture like this. But since now we have, we remember that we have two types of hexagon, and we can apply in principle both types, but let's just for convenience apply one of those. So we can say that here you have 2, 3, here you have 1, 2. So here you have 1, 2, 3. And this upper guy is 1, 2, and 3. But now at the second step, we can connect these two guys here, and they're just commute because there are no repeating index here and here. All indices are distinct, and we can just commute them by square. Here is 2, 3 again, and this is 4, 5. And it remains now to connect 4, 5 and 1, 2, 3. And again, so since there are no repeating indices, we can just close it up as a square. And then we eventually computed what we wanted. So we closed it up, this relation. So here we have 4, 5. So this is 4, 5. This is 4, 5. And here we have 1, 2, 3. Yeah, and the statement is that such an algorithm you can try to do by hand, some examples, and it always works. So we have proven that, and but this is not unique. So in principle, well, as an exercise, you may change here. Check, for example, type 2 hexagon. And in principle, if one can play with different tiles, you can see that there are, in fact, quite a lot of possibilities, especially when such sequences are large. But you know that they always can be constructed in this finitely many steps. Any questions? So, with some discussion. Yeah, so now let's proceed some more interesting things using unlinking, what we can do. So now we can define permutohedron from unlinking. And once again, this is very general construction. So in principle, if you heard about permutohedra in the context of not Quivers correspondence, so this is much more general, but those permutohedra, they could be deduced as the special cases of this construction. But in the last lectures, I will still speak about not Quivers. So then for the moment, I wanted to introduce you first this general construction. So, and generally, yes, let's just consider an example first. And so the question is, for example, if you have pentahedron pi 2, it's just so yeah, maybe I need to put some different notation. So this is, yeah, maybe I need to use square brackets. So this is just the notation of permutohedron. So we have nodes which are organized by these tuples. And for example, if you have a permutation here, so we have a permutation 1, 2. So pi 2 essentially is a pair of nodes connected by an edge. And now we want some quivers. Here we want Q, and here we want some Q, which we label essentially by these tuples of integers. So we here want one Q1, 2, here we want to Q2, 1, and we want them to be equivalent. And this equivalence effectively, so how can we generate such quivers? So we can start so very simply. So this is basically what we had before. So we have hexagon relation. So let's start. Maybe I can write some generic quiver Q here, and we can apply unlinking twice. But unlink what? So you need to put some index iota. So this would be some distinguished node in Q. So we have an assumption that Q0, so the set of nodes, includes some distinguished index iota, and here should be also J1, J2. So this indices would be responsible for permutation. So this 1 and 2 would be associated to these two nodes and maybe something else. So we don't really care about the rest. So this is for Q. And unlinking now Q at iota and J1 on one side and iota J2 on the other side will give you, well, some quivers. Okay. Yeah, and this is step 1, and step 2, now we apply exactly the same unlink as in the hexagon. So now we unlink J1, J2 here, iota J1. And you see, since we have a permutation here, so first apply J2 and J1. On the left and on the right, we apply J1 and J2. So then in principle, one can identify quivers in permutahedron with such pairs. So here we have 1, 2, and here we have maybe just another way around. So 2, 1. Here we have Q 1, 2. So now we say that these two quivers, they form permutahedron of order 2, and this dashed line denotes that this is a permutation, and maybe I need to put the same dashed line here and this red. Just to distinguish these two types of diagrams. So this is dashed for permutation. And we, of course, know that these two guys, they're equivalent. So here, simply because we have started off from the same quiver, and we just unlinked it, and all these quivers in this diagram, they're equivalent, but we also know that we can connect them by applying unlinking once more. Yeah, but what we can also do is we can also take this iota and just remove it. So because of course iota is still present here in these quivers. But we can simply remove iota from all quivers that we had here in this diagram. So this step, remove iota, and what we obtain. So the statement is that we only obtain this top part. And here we have some Q prime to 1, Q prime 1, 2. And these are still connected by permutation, and you can still unlink them to the same quiver. And the reason for that is that, okay, by removing of iota, we essentially cannot complete this diagram because here we had step which involved iota. So this unlinking involves iota, this unlinking also involves iota, and if you remove it, then this is forbidden. So we just get rid of all these quivers that we have on the bottom. But this step, the last step in the hexagon, maybe let me just go back to the definition of unlinking hexagon. Yeah, so here iota has been a repeating index here. And for example, for type 1 hexagon, which we use to generate permutohedron of pi2, so the repeating index was j. And j is not applied here, nor here. Yeah, but j still applies here and here. So therefore, if you remove j, we cannot undo these unlinkings that we had on the top, and we only left with this triple of quivers here on the top. And for type 2, this does not quite apply because here we permuted unlinkings these two guys. And oh, Elder, can you please mute yourself? There's some noise. Yeah, thanks a lot. Yeah, so by permuting these two guys, then you cannot quite build up a permutohedron from this diagram. But it works nicely for this type 1 hexagon. And then it admits a nice generalization. So maybe I can ask Piotr, can I have maybe 5 or 10 more minutes just to explain?
Yes, no problem.
Yeah, that's perfect because I was a bit low on time today. Yeah, so for the simplest permutohedron, we can just use this hexagon relation. And yeah, so this is yeah, what works for any pure cube. And let me just maybe to make it more solid, so to show you the next more complicated example. So let me maybe even show you. So I'll stop sharing screen for a moment because I want to show slides, just not to draw all these diagrams all over again. Can you see the slides now?
Yes.
Yes, so now we want to mimic this construction, but let's consider the next case when our goal is to construct a permutohedron of order 3, which is shown on this slide. And now we do the same. So essentially, we start with some quiver. And again, we have distinguished index iota. And now we have a triple of indices j, k, and l. And we apply 3 unlinkings. And then so for every path here, we just permute I, j, and k. So all such paths, they're just permutations. So here we have L, J, K, iota L, iota K, iota J, and so on and so on. And now the statement is that the resulting 6 quivers would form permutohedron pi 3. And to check also the equivalence, well, of course, you have it manifestly, but for more nicer somehow presentation, we can start to fill in the interior of this permutohedron by connecting all the missing connections here. So we can first, for example, apply a hexagon relation to each of these quivers, so each of these branches, and then this closes up like this. And now we can also continue like closing up like these quivers here, and eventually this is closed like this. And yeah, so what we have done, eventually we construct this perimeterhedron, and this is styled now by squares and hexagons. And yeah, so now you see that these are nodes which are highlighted. These orange nodes, they form perimeterhedron, and you can unlink each pair which is connected by an edge or by permutation. You can unlink them once more to the same quiver. And in order now to relate this construction to nodes, so I will slightly go forward, just for the next lecture, to make a reference. So to connect this to nodes, one is essentially removes iota from all these quivers that we have. And then the resulting quivers, so essentially you destroy all that we had in the interior of this diagram. But what survives are these orange dots. And you can see that unlinking which connect orange dots, they do not involve iotas. So here, this index, for example, iota k is different from iota. So iota k is the node which has been created by unlinking iota and k, and this is completely dependent from iota. So if you remove the node iota, so this node still survives, and j, of course, and k, and so on and so on. So this is like the main idea how one can build up a general perimeterhedra for arbitrary quivers. And yeah, maybe for today I would finish, and if you have any questions.
We already passed the time, so maybe let's try to move them to Monday unless they are very urgent.
So we use the chat message.
So I think the chat message was the earlier one from She. Okay, and again, official announcement, the continuation of the talks. The last two will be merged into one long talk, which will take place on Monday, 1 p.m., the same Zoom link. You will also get a newsletter with this link. This link will be in the official newsletter. It is the same room as this one. It was already in the last newsletter, this link. This is the same room. So Monday, 1 p.m. So thank you very much.
Thank you.
Thank you, Dima.
Yeah, see you on Monday then. Bye.